Now that we've seen what a multivariable function is, basically a function that has several independent variables, we're going to go back and review a lot of the things that we did in Calc 1 and see how it changes when we have extra dimensions to work in. The first thing we looked at in Calc 1 was basically limits. So let's take a quick look at Calc 1 limits and see what has to change when we go to Calc 2. Now remember the idea for a limit in Calc 1. Let's call that L. So, I missed a little bit there. All right, so here the idea is if this is some function f of x, we could say the limit as x approaches c of f of x is equal to L. Of course, from this picture, kind of. I missed a little bit. All right, so what does this mean? Well, the idea was anytime we're talking about a limit in Calc 1, we're always talking about two one-sided limits built into this. Because since we're approaching x equals c, and we're only doing that on the x-axis, we can actually only approach it from two different directions. We can either approach c from values bigger than c or less than c, but solely on the x-axis, because that's the only direction that we can move. Now, of course, as we approach c from the left and the right, you can see that the function from the left is heading up to a value of L, and from the right is heading down towards a value of L. Now, that's how we approach it. Now, there is a mathematical definition that you may or may not have covered in Calc 1, kind of depends on where you took it at. That here's the actual definition that a limit exists. It says, if the absolute value of f of x minus L is less than epsilon, when x minus c is less than some delta. Okay, here, what does this say besides some scary stuff? Well, first thing let's notice is these two new letters, that's a C by the way, this epsilon and this delta, those are two arbitrary values. And generally we assume that they're arbitrarily small. As engineers, you kind of want to think about this as a tolerance. Let's say that I want the distance between the actual function y value and the y value of L to be within 0.01 meters of each other. Well, can I always make it happen? The idea is, can I get close enough to C on the x-axis to where every single y value falls within that window? Well, let me redraw the exact same picture. Let me get the blue stuff off there. And you kind of get the idea of what this is talking about. There's my function, there's C, there's L. So this is saying is the distance between x is c, so here this would be c minus delta, c plus delta, creates this little window up here. And as long as the distance between x and c is less than delta, so that's inside this window, are all the y values up here, so this would be L minus epsilon and L plus epsilon, I think my picture is a little bit wrong, are all the y values inside of there? Oh, it's close up there. So notice for here, if we pick this particular value of epsilon, whatever it is, all the y values, it's really close right there, all the y values fit within inside that window, which means I can pick any epsilon I want that shrinks the window this way, as long as I can find the delta, no matter how small I make this at, that means that this limit has to exist because I can squeeze this window down until it gets infinitely small on that point. Proving a limit exists using this definition, I'm not going to go into today. Again, depends on where you took calculus at. You may have been shown how to do that or not. Well, unfortunately, it's not quite as easy when we add a different direction. And here's the sole reason why. Now we're going to take a look at a limit. Now we have both x's and y values. So we're going to take the limit as xy approaches some value, I'm just going to use x naught, y naught, of some x and y. So this type of limit, what are we talking about? Well, instead of looking at what happens to y values as we approach an x, now we're taking a look at what happens to z values as we approach a point in the xy plane. So we have some surface up here. There's our surface. There's our z equals f of x and y. But what we're looking at is down here in the xy plane, x naught, y naught. So we want to know, kind of if you can track this up here, that would be f of x naught y naught the way I have it drawn. What happens to the z value as we get closer to this point in the xy plane? But here's the huge difference. When we're solely in the xy plane and there's our point, x naught, y naught, there's more than just two ways to approach that point. We just can't approach from the left and the right anymore. Now we can approach from any direction and along any path, which means I can approach it from the left. I can approach it from a straight down. I could go along some weird wavy curve and get in there. I could go all the way around and go back that way. There's an infinite number of paths to get to that point. So unlike in Calc 1, where really all you had to do is check the limit from the left and see if it was the same from the limit from the right, now we have to check all possible paths, which generally is horrible to do. So we're going to kind of see how we're going to adjust that for this semester. Now there is a definition, just like before, but it's a little bit uglier. Let's put an L there. It still says if the distance between this and L is less than epsilon, when, now here's the big difference, it's just not the distance between X and C on the number line, it's the distance from all the points to a single point in a two-dimensional plane. So basically a circle of points around it. So that would be the square root of x naught squared plus y minus y naught squared has to be less than delta. All right, so quite a bit more complicated because now we got to take a look at all the different ways we can approach this point. So we're looking at a little circle around them. Now, we do get some good news here. By the way, you're going to explore this more in classes in the future, especially for those of you that want to go get a degree in math, and you're going to see how to actually use this to prove that the limit exists. We're not going to go through most of that this semester. We're going to just take a look at a couple of cases. First off, how do we actually evaluate a limit when we have a multivariable function? So if I were just to say, what's the limit as xy approaches 2, 3 of x plus y over x squared? Well, here's the great news. Exactly the same way you would have done this in Calc 1. In Calc 1, excuse me, you always do direct substitution first. So if we try direct substitution, that's 2 plus 3 over 2 squared, 5/4. If you get a number out, you're good, you're done. So you always want to try direct substitution first. That goes without saying. Now, unfortunately, the same types of things can happen when we're dealing with limits that may or may not exist. Let's take a look at something quite a bit more difficult. xy approaches, let's say 0, 0. Let's do x squared minus y squared over 2x squared plus 5y squared. Okay, so if we're given something like this, again, we'd want to do direct substitution. Now, hopefully it's easy to see direct substitution for this would give us 0 over 0. The exact same idea in Calc 1, that tells us nothing. This limit may exist or it may not exist. Proving it does and doesn't is a little bit more complicated than I want to go into this semester. So the way that I'm going to ask you to do this for this semester is, I would say, prove the limit does not exist. So notice I didn't say find the limit. I'm making it a little bit easier for us, and I'm just saying prove that this limit doesn't exist. Well, in Calc 1, how did we prove a limit didn't exist? All we had to do is show the limit from the left didn't equal the limit from the right. The limit didn't exist. Well, we're going to do almost the same thing, but it's going to be a lot harder. What we're going to do is we need to show that two different limits don't exist. Now remember, when we're approaching a point in the xy plane, we can approach it from any direction that we want to. It doesn't matter which way you approach it at or what path you go along. So basically our goal right now is to find two different paths that lead to two different results. If you take two different paths and you get the exact same result, that doesn't mean the limit does exist. In fact, if you got the same result an infinite number of times, does not mean the limit exists, because all you got to do is find one that they don't exist, or that they're not the same, and then it will not exist. So here's what I mean. Let's take a look, and here's our point. We're approaching 0, 0. So there's where we're approaching in our xy plane. And I can approach through any path I want as long as the path goes through the point 0, 0. Two pretty common ones. Let's try path 1. One common path is to let one of the values equal 0 and then approach it there. So path 1, let's let y equal 0. Doesn't matter. So if y is equal to 0, now this is where it gets a little fuzzy kind of thing here. Y equals 0, which means we're approaching along the x-axis from one side or the other. It doesn't matter which way you did this. Technically, you're doing both. So we're approaching along the path y equals 0. So if we're going y equals 0, then this becomes the limit as x0 approaches 0, 0. Right? Because in this case, y is already 0. So it's not x and y, it's x and 0. And what does our function become? Well, that's x squared minus 0 squared all over 2x squared plus, what did I say, 5 squared? So we want to know what the limit as x0 approaches 0, 0 would be. Well, that's just x squared over 2x squared. Limit as x0 approaches 0, 0. Well, that's 1/2. And of course, the limit of a constant is that constant. So if we approach this function over here along the x-axis, we're heading towards 0, 0, we get a value of 1/2. No matter if we're coming from the left side or the right side, we still get that 1/2. Let's try a different path. Again, a very common path is do something like this, now y equals x. Now, got to be careful, the path you pick has to go through that point. So the line y equals x is this line right here. The diagonal line here. So in this case, we're approaching it from, well, either side here. So if we approach it along the line y equals x, it means, well, y is equal to x. So this becomes the limit as x approaches 0, 0 of x squared minus x squared all over 2x squared plus 5x squared. So notice all I did is I replaced all the y's with x's. Well, what happens here? Limit as x approaches 0, 0. X squared minus x squared over 2x squared plus 5x squared, or the limit as x approaches 0, 0 of 0 over 7x squared, which is 0, right? That's just going to give us a constant, which is 0. So notice, as we approach the function along the line y equals 0, or the x-axis, it's heading towards a value of 1/2. But if we head along this line, y equals x, the z value is heading towards 0, which means the limit does not exist. Now, if we would have chosen something else, like along the path, I don't know, x equals 0 instead of y equals 0, and we got the same value here, if we got 1/2 for both of these, let's say, that doesn't mean, again, does not mean the limit exists. It just means you need to pick another path to see if you can get a difference. Now, the number one mistake that students make here is they pick a path that doesn't go through the point. Like, I couldn't pick the path y equals 2, because y equals 2 is up here, right? That's the line y equals 2. That doesn't go through where we're going, so that we can't take that as a path to get there. So make sure that you're taking the correct path. You could even do this, y equals I don't know that you want to, but y equals sine of x goes through that point, so that would also work. All right, so if you're told to prove a limit does not exist, find two different paths and show that they get two different values. Just so you know, two really common type paths for this level is let one of them be 0 and then let them be equal to each other, but do make sure it goes through the same point. So you see, we have a lot of commonality with our limits. We generally just want to do direct substitution first, and then if you get 0 over 0, you're generally going to be proving that the limit doesn't exist. All right, one more thing we want to talk about is continuity, and this is really just going back to the definition we actually already talked about once this semester. Like I said, in Calc 1, we had 3 different parameters for continuity. So in Calc 1, we said that the function exists, I'm just going to say it's c, to the limit as x approaches c of f of x exists. And the third case was that the limit as x approaches c of f of x is equal to f at c. All right, so these were our 3 things from Calc 1 to show that a function was continuous at a single value c, which is kind of weird to say, but at a single value. Now, if you wanted to show that something was continuous over an interval, you had to show that this was true for every c value in that interval. However, we kind of streamlined this just a little bit, because you can see the last line kind of includes these two. These two can't be equal to each other if f of x doesn't exist at c, or if the limit doesn't exist. So if you assume that if you end up with a true statement that includes both of these, this is really only the idea that we need to be continuous at a point, which means the exact same thing occurs when we have multivariable functions. So it just looks a little bit more complicated. So for continuity, okay, so a function is continuous at a point if the limit of the function as it approaches that point, x naught, y naught, of the function f of x naught, y naught. Right, same idea. So that means that it's continuous at a point. If you want to show that it is continuous over a domain or a whole region where x's and y's exist at, you have to show that this is true for every value in that domain. So generally when we're talking about a domain, we're talking about x and y's. So if we wanted to show it was true for everywhere inside a circle of radius 5, you'd have to show that this is true for every point inside there. Now again, most of the time we just kind of do some hand waving for that. Let's see, let's try. Prove f of x is equal to, I don't know, prove f of x and y. Sorry, f of x and y equals sine x plus y is continuous in the region x squared plus y squared is less than or equal to 25. Okay, so we have some function of x and y here, and it's just sine x plus y. Show that it's continuous in the region x squared plus y squared equals 25. So here's the way you would do it. Let x naught, y naught be any point in x squared plus y squared less than or equal to 25. So basically we're just saying, I'm going to pick an arbitrary point, any point somewhere inside that circle. Then I'm going to take a look at the limit as xy approaches x naught, y naught of our function. Now we always try direct substitution first, and of course if I do direct substitution, this is just the sine of x naught plus 1. All right, now here's what I mean when we kind of do just a little bit of hand waving. Now we're going to examine this function. Does this function exist for every x and y value in this interval? And of course the answer here is yes, because sine is what? It's continuous everywhere. So it doesn't matter what you plug in there, this will give you a correct answer. So we could say yes, this is continuous for all values. So x naught plus y naught exist for all y naught and x squared plus y squared is less than or equal to 25. Good. So since that exists for all those values, then you know that it's continuous over that region. In fact, since it's continuous for any values, this function, our original function, is actually continuous for all the values in the xy plane. All right, so it's basically the same thing we saw in Calc 1. We just added an extra letter when we do it.